A word of warning about computing the instantaneous rate of change of a function. We previously saw how to compute the instantaneous rate of change. We basically compute the average rate of change over a sequence of smaller and smaller intervals. So for example, if we have f of x is equal to e to the x, and we want to estimate the instantaneous rate of change at x is equal to 0. So we can make a table and consider the average rate of change over the interval 0 to 0.1, or 0 to 0.01, 0 to 0.001, 0, 0.0001, until we see what happens as those average rates of change level out to a particular value. Now you may be tempted to just start with a ridiculously small interval. What if we just skip all that and just say, well, what's the average rate of change between 0 and 0.0000001? Well, as it turns out, you might get the wrong answer. So instead of going through all those details by hand, I have a spreadsheet here. And so basically we'd like to compute, the average rate of change. So we have f of x is equal to e to the x, and we want to compute the average rate of change between, let's say, 0 and a, and then see what happens as we change the point a. So the average rate of change between 0 and a will be f of a minus f of 0 over a minus 0. So it's equal to e to the a minus 1 over a. So let's see what happens to this as we choose different values of the number a. So let's start off with an a. So my first column will have just a, 0.1, and then we'll say is equal to this divided by 10. So we'll keep reducing a by smaller and smaller amounts by a factor of 10 each time. So the average rate of change is going to equal e to the a minus e to the 0, which is 1, divided by just b2. So that's the average rate of change between 0 and 0.1. The average rate of change of e to the x between 0 and 0.1. And if I copy this down like that, I see that 1.005016784 is the average rate of change of e to the x between 0 and 0.01. So a spreadsheet's a very useful tool to quickly come up with the average rate of change of many of these. So I can just keep pulling these formulas down. So 0.01 got divided by 10. So we see now that the average rate of change between 0 and 0.001 is 1.0005, and then some stuff after that. So it's looking already like the average or the instantaneous rate of change of e to the x at the point x is equal to 0 should just be 1, because it looks like the average rates of change are leveling out at 1. Well, let's see if this pattern persists. So between 1 or 0 and 0.0001, it's even closer to 1. Even closer to 1 still. Well, let's see. We have 1, 2, 3, 4 zeros. 1, 2, 3, 4, 5 zeros. Definitely closer to 1. Closer to 1 again. Closer to 1 again. We are up to 1.00000000. I wasn't counting those. 1, 2, 3, 4, 5, 6, 7 zeros before the first non-zero digit after 1. Now we've kind of flipped to the opposite side of 1. That's not necessarily a bad thing. Just so we have a common reference frame, let's just add a new formula. So this is equal to the average rate of, well, let's say, the absolute value of the average rate of change minus 1. So this is how far away the average rate of change is to 1. So you can see it is indeed still closer to 1 than before, even though it's on the other side of 1. So let's keep making this interval smaller still. So we make it smaller again. It got a little bit further away from 1. It used to be this far from the number 1, and now the average rate of change is further from the number 1. Well, that's weird. Maybe it's a little fluke and it will go back down. It hasn't gone back down yet, even though we have a 100 times smaller interval here than we did up here. It's still further away from 1. Now it's really further away compared to where it was up here to here. It's a lot more further away from an average rate of change of 1. You can see there's only 4 zeros before we get non-zeros. Now it's even further. It's just getting worse. So it's not leveling out at 1. And here it's about the same. Now it's really worse. We get 1.11. So what does this mean? Does this mean that the instantaneous rate of change isn't 1 after all? It's actually 1.11 or maybe something else entirely. Let's go take it a step further. 0, average rate of change of 0 between 1 or between 0 and 10 to the minus 16. So that's really far off from what we thought. We thought it was leveling off at 1 up until this point. And then it just got worse and worse and worse, and now it's just all over the place. As it turns out, the instantaneous rate of change is really just equal to 1. And what you're seeing here, why it's getting worse when we get down here, is because when the computer does these calculations, it truncates. It only keeps so many digits of the values. So when you compute e to the 10 to the minus 13th, the exponential of 10 to the minus 13th, there's a lot of zeros there, and you're only getting a couple things. So there's not a lot of difference between that and e to the 0. So you're losing the precision, and you're getting a bunch of basically computer error down here. So you might be tempted on your calculator to just choose 10 to the minus 10th and just go between, if you were estimating the instantaneous rate of change at x is equal to 3, and then 3.000000000000001. But you might get the wrong answer because you chose too small of an interval, and the your calculator's truncation error is giving you a skewy answer. So it's usually best to start with rather modest interval to do your average rate of change between, like, say, 3 and 3.1, or in this example between 0 and 0.1, and then let it become smaller and smaller, and you'll see where it's leveling out. The average rate of change is leveling out towards I don't know what that was about, towards 1. And then when it goes screwy, you ignore that, because that's just truncation error. So always, make the table and look at what's happening to the average rate of change over a sequence of smaller and smaller intervals. Don't do it the quick way and just take a really small number and throw that in, because you might get the wrong answer.